Paxos. You've probably heard the name whispered in computer science circles. It has this reputation for being one of the most important, but also one of the most brain-meltingly difficult algorithms out there. But here's the funny thing. Its creator, Leslie Lamport, insisted it was all very simple. Today, we're going to take him at his word. Let's make Paxos simple.
So what's the big problem we're trying to solve here? Well, think about the servers that run your favorite online service. They're spread out all over the place, and they all need to have the exact same picture of your data. But what happens when messages between them get lost or show up late? How in the world do they all agree on one single truth? This right here is the consensus problem, and cracking it is the key to building any distributed system you can actually rely on.
And to get there, we're going to take it step by step. Here's our roadmap. First, we'll nail down what consensus really means. Then, we'll look at a really simple, obvious solution and see why it completely falls apart. We'll then get to the first aha moment, the big insight that starts to fix things. That'll lead us to the core two-phase solution of Paxos itself. And finally, we'll see how agreeing on just one little value lets us build absolutely massive, reliable systems.
All right, so first things first. What are we actually trying to achieve? The whole goal of a consensus algorithm is to get a group of computers to pick one single value out of a bunch of possibilities. And once that value is picked, the computer should be able to find out what it was. Sounds easy enough, right? Well, as we're about to see, the devil is absolutely in the details.
Before we can even dream up a solution, we have to establish the rules of the game. These are the non-negotiables, the safety requirements. Rule 1. The system can't just invent an answer. The chosen value has to be one that was actually proposed by someone. Rule 2, and this is the big one, only a single value gets chosen, period. No split decisions. And Rule 3, a computer can't be tricked. It should never ever learn that a value was chosen unless it really truly was. These 3 rules are the bedrock of trust for the whole system.
Now, to understand how this all works, we're going to break it down into 3 roles, or agents. First up, we have the proposer. This is the agent that gets the ball rolling. It's the one that suggests a value that it wants the whole group to agree on.
Next, we've got the acceptors. You can just think of these guys as the voters. Their job is to listen to the values being suggested by the proposers and decide whether to accept them, to cast their vote. The final decision of the whole group is going to come down to what a majority of these acceptors decide to do.
And finally, there are the learners. Once a value gets a yes from a majority of acceptors, it's officially chosen. The learners are the agents whose only job is to find out what that final chosen value is. Now, in a real system, a single computer often plays all 3 of these roles at the same time, but thinking about them separately makes this whole thing way easier to grasp.
Okay, so we've got our rules, we've got our players, so how do we actually pick a value? Let's start with the most obvious, common sense ideas and see why they don't quite cut it.
The simplest possible approach? Just have one acceptor, a single decider. The first proposal it hears wins. Done. It's simple, it's fast, but if that one acceptor crashes, the entire system grinds to a halt. It's a single point of failure. Okay, so let's fix that. Let's use multiple acceptors, and we'll say a value is chosen if a majority of them agree. Great, now we can tolerate failures. But this introduces a brand new, much more subtle problem: deadlock.
So what is this deadlock problem? Well, imagine 2 different proposers suggest 2 different values at almost the exact same time. Value A gets accepted by, say, half of the acceptors, and value B gets accepted by the other half. What happens now? No value has a majority. No decision can be made. The system is just stuck. It's completely frozen, unable to move forward or backward.
So how do you break a tie like that? How do you get the system unstuck? This is what leads us to the first major breakthrough in the Paxos algorithm. It's a way to create some order out of all that chaos.
The insight is just beautiful in its simplicity. We're going to attach a unique number to every single proposal, and we'll just make sure that these numbers always go up. Now the acceptors have a dead simple rule to follow. If you see 2 different proposals, you only pay attention to the one with the higher number. This lets the system tell the difference between old ideas and new ones, giving priority to whatever's happening right now.
This higher number wins rule is great, but it creates one final, really dangerous trap. Imagine a value, let's call it V1, is so close to being chosen. It's just one single vote away from a majority. But before it can get that last vote, a brand new proposer jumps in with a higher proposal number and a totally different value, V2. The acceptors have to follow the rule. They have to listen to the higher number. And now, V2 might end up getting chosen instead. We could have two different chosen values, which completely shatters our most important safety rule.
And this right here brings us to the core mechanism that makes Paxos actually work. The solution to this final, tricky problem is a clever two-phase process that guarantees safety. This is the heart and soul of the algorithm. So, what's the key? The whole idea boils down to this. Instead of a proposer just blindly shouting out a value, it first separates the process into a promise phase and an action phase. It's kind of like asking for permission before you actually do something.
So, phase 1 is the prepare and promise stage. A proposer picks a proposal number, let's call it N, and sends a prepare request with that number out to the acceptors. It's not proposing a value yet, it's just reserving the number. Then, a majority of the acceptors reply with a promise. They're promising not to accept any older proposals with a number less than N. And, this is the crucial part, they also report back if they've already accepted any value in the past and tell the proposer what the highest numbered one they saw was.
Okay, once the proposer gets promises back from a majority, it's time for phase 2. Now it sends the actual accept request. And here is the absolute genius of Paxos. If any of those acceptors reported a previously accepted value, the proposer must propose that value, the one from the highest numbered proposal it heard about. It's forced to adopt the group's history. It's only free to use its own value if no one reported anything back. This guarantees that if a value is already close to being chosen, any new proposal will help push it over the finish line, not start a brand new race with a different value.
So we did it. We found a safe way for a bunch of computers to agree on a single value. That's a huge achievement. But how do we go from this one little building block to constructing the massive, reliable systems we use every single day? The answer is, we just run the algorithm over and over again. We use one instance of Paxos to agree on the first command in a sequence. Then we run a completely separate instance of Paxos to agree on command number 2, then a third for command number 3, and on and on. What this does is it builds a consistent, ordered log of commands, an identical history across all the servers. This is what's known as a replicated state machine.
And that replicated log, that's the foundation for so much of the technology we absolutely rely on. When you're using a cloud storage service, a modern database, or pretty much any critical online system that just can't afford to lose your data, there's a really good chance that deep down inside, an algorithm like Paxos is constantly at work, making sure every single server has the exact same correct version of history.
So the next time your files are perfectly synced in the cloud, or an online transaction just goes through without a single hitch, remember what's really happening behind the scenes. It's not just a bunch of code. It's this elegant, invisible dance of proposers and acceptors all reaching a majority agreement over and over, all just to keep our digital world in perfect working order.